some people are probably not excited. Outside, it's a little hot, it's a little sunny. Maybe it's a little uncomfortable for you, you don't really like, you can't see your screen very much. I'm just going to make sure that this is out there before I start. I don't even care about that at all. Your level of discomfort matters very little to me. The only thing I care about is I want to teach you this the way that I feel like is the best way, and this is the way I decided to do it. And sometimes you're going to be a little bit uncomfortable, but like whining and complaining about outside, that's not a thing for me. This is how we're going to do our day. You can handle it. You guys feel good about that? Excellent stuff. I want to talk about some of the fundamental things. We're going back to like 6th grade, 5th grade, junior high, freshman year type of information, but we want to start this conversation with one of the most elemental foundation cornerstone points so that when we get to the more complex stuff, we can break it down and make sense of it. We're going to hack climate and weather, which is one of the biggest systems that occurs on our planet. It's also one of the most important systems. It's governed by a few basic rules. If you know those basic rules, you can figure out why forests are where they are, where deserts are, why every organism that exists on this planet is where you find it. It's the cornerstone of evolution. It's the cornerstone of natural selection, all of those things. So we're going to start at the very beginning with one of the most easy parts of it. So, the first thing I want to talk about today is energy. I drew a picture and I wrote some things, definition-wise. Energy is one of these simple definitions. It's a really easy thing to think about. I'm just going to hold this up and walk since this is a strange environment. It's only like a 5-sentence definition, and I drew some symbols around it to try to help us make sense of it, but it's a really loaded word. So what I wrote here is, energy is the ability to do work. So energy, it means the ability, we can do something with that. So these words, ability and do, kind of go together in my mind. Work is another word that's kind of complex, which we'll dissect in a second. And so energy, we're going to be able to do something. I need to have something in order to do something with it. Wouldn't you agree with that in the most pure sense? So if I want to do work, I want to have the ability to do work, I have to have something. So energy is going to be an amount or a quantity. That's going to be a universal truth. You'll see that many times. It's going to be expressed as an amount of something. So energy is the ability to do work. Here's my beautiful picture. I'm like the worst artist, but it's fine. You can figure it out. There's a little block here somewhere, and then it's tied to a string, and then on the other side of the string, there's a truck. And the truck has the ability to do work, wouldn't you say? In a couple different ways. It's kind of hard to see on here. I know the picture's small, but one of the things the truck can do is drag the block. If the truck drives forward, it can pull the block across the ground. That's one type of work. It's probably the most obvious. But I also drew, there are headlights on the front of the truck. So there's light right there. Light is also energy. I also have some music notes because this guy is pumping the radio hard. Music has the ability to do work. So there are many different things that can do work. We can do it through light, heat, music, sound waves. We can do it physically. We can move something across the ground. All these qualify as work. So as a picture, this feels like a very comprehensive definition of work. Everybody feel good about that so far? Energy is the ability to do work. Well, so I've circled a few things and I've boxed a few things. Let's break those down because we started simple. Now we're gonna move. So I want to look at this definition that was the one that I underlined on the previous page. Work. So if energy is going to be a quantity and we want to figure that out, then let's break it down into its elemental parts. So work is going to be the force. So we're going to be pushing or we're going to be doing something and it's going to go across a distance. So when we write it out, that's going to be energy. That's the total amount, right? That's what it's going to equal, this work side. And it's going to be expressed as the amount of force over the amount of distance as a ratio. I need 2 people to help volunteer for me. I got one right here. One? Beautiful. All right. Come on up, guys. All right, so you can check out that definition for a second. Here's what we're going to do. I need you to take this, and then come on over. Or here, come over here, walk over. We're going to measure this up. Okay, so we'll start right here. I'm a huge fan of textbooks, so I didn't want you to get the wrong idea. I'm going to use our textbook for this demonstration purposes, but I didn't want to destroy it, so I put it inside of this stuff. But our textbook is in there. You can see it. It's actually an old copy of the textbook. So I like textbooks because they help us learn. So we're going to use this in an unconventional way to help us learn. So what's the definition of work again? Can somebody give it to me?
Force times distance.
Force times distance. So when we're looking at energy and we're talking about it as a quantity, you guys know this. Like I said, we're going back to 6th grade. Things can have potential energy or if they can have kinetic energy. So which has more potential energy? The book here or the book here? This is super easy. 2, right? When it's up in the air. And why is that? What is the force that we would be working against that would give this energy? What's going to drive this book? Gravity, right? So there's a gravitational force that's bringing this down. When it's closer, it's not pulling on it as much. As we move it farther away, the force is going to pull that down. So it has potential energy, and it has more potential energy as we go up. So if we want to look at energy as a quantity, we're going to think about the force over the distance. So the force is gravity, and the gravitational force for a book of this weight and this size, this place on Earth we're at, is going to be 4 newtons, okay? So you can write this down and work your way in the easiest sense through the calculations. So 4 newtons, that's the force side. Everybody got it? Great. Okay, so now I'm going to do a little bit of work. If the book is here, and I want to move it up, so somebody just hold the tape so that that end is on the ground, and then hand me the other end. Put that on the ground. This one goes on the ground. This on the ground. Okay, so I'm going to do a little work by moving the book up here. So we're working against gravity. I'm going to go up. This is a little risky. Hold the ladder. That's what you're here for. Woo! Let's see. Where are we at? Oh, here we go. This is 3 meters from the ground. So, what are you going to write down for the work? What's the equation? I can't hear anybody. We got 4 newtons, that's the force, times the distance. Wait, what are you lifted up for? Yeah, but I'm like in the air, man. Give me a break. Okay, so if we're going to do a little work, what is the work that's going to be done? What do you think I'm going to do? Guess. Huh? It should be 12 joules, right? So the work of the book going up here is 12 joules. And then we can see that it has energy. We can express it just like that. Does this make sense? So, thank you. Stay here, though. So we've got work equals force times distance. The force was 4 newtons. The distance was 3 meters. So the answer in this case for work, we're going to express it in the form of joules. So that's going to be 12 joules. So work here equals 12 joules. 4 newtons times 3 meters. Everybody got that so far? All right. You guys feel good about work so far? There's a lot of different ways that I can do this process, okay? So here's the book. I can do it the easy way. So you can count, right? You got a loud voice? Sure. Okay. You're going to count how long this takes, okay? I'm going to do this. I'm going to go up 3 meters. You ready? Tell me when to start.
3, 2, 1, go.
I'm guessing on 3 meters, somewhere about like, right? I got it.
7.5 seconds.
7.5 seconds. So that's one way to do the work. Hey, can you do me a favor? Put that on the ground. Now, I'm going to have to throw it to you. Come over here. Woo! Getting sketchy. Hold the ladder. All right, put it on the ground because we got to keep everything equal. And I just want you to throw it up, and I'm going to catch it right here. Let's practice once without the timing. You ready? 1, 2, 3. Woo! Great. Again like that. So you got the time. All right. On your mark, get set, go. How much time? 1 second. 1 second. So, was the same amount of work done? Great, you guys can sit down. Was the same amount of work done each time?
Yes.
Because what was the work? What's our definition of work?
Force times distance.
Force times distance. We went up 4 newtons. That's the force. Gravitational force working against that. 3 meters should be 12 joules. So we have to understand, because there's definitely a difference between those two things. And that difference is this third definition that I'm going to give you right here, known as power. So power is going to be expressed like this. Power is the amount of work, 12 joules, divided by the amount of time. So one of them was 1 second, and the other was 7.5 seconds. Do the math. What does that equal? It's going to give you some number. It's 12 joules divided by 1, and then 12 joules divided by 7.5. I want to use those numbers, so do the math. Give me the one for 7.5.
1.6.
1.6, and then what was it for the 1 second? Should have been easy, right? Should have been 12. Okay, does everybody understand work, power, and energy up to this point? We're still cooking? We're still good? All right. So now that we've seen this, the application of the force, which is the way that we did that, the way that we executed it, tells us a little information. So if you do 12 joules in a second, like the way that we threw it right there, that's equal to 1 watt. You don't have to have these memorized, but I want to think about these as numbers because we'll come back to energy many times. So a light bulb, if it needs 60 watts to turn on, you need 5 times as much energy as I just threw up there. That same amount of energy, like we talked about in the laboratory sense yesterday, I can also use energy and think about it in terms of heat. And 1 calorie is the amount of energy to bring 1 gram of water up by 1 degree Celsius. So 12 watts of energy is also equal to about 3 calories. So when we threw it up in 1 second, I could have also used all that same energy, and I would have had to do it in a different manner, but I could have heated up 3 grams of water by 1 degree Celsius. Those are all interchangeable, right? Because the only thing we're thinking about is doing something, we're applying force across a distance or to do some kind of thing, and then power is how quickly or how well or how efficient we're doing that process. Everybody okay so far? All right. Very good. So, we're on these definitions. We need to move around a little bit, which I know it's hot, but I don't care. So everybody stand up. Everybody stand up. Just leave your stuff right there and come out into this space. Come on out. We're going to model something very easy. Check out my drum. Like it? I'm the only person who would bring a drum to school for a definition. So, this motion, we had potential energy, but we saw examples of kinetic energy, right? Of movement of things. So heat energy is exactly like moving that, like moving the book. It's kinetic energy. Does that make sense? So here's what I want to happen. We're going to do a little demonstration. You guys are all going to be molecules. We're going to represent kinetic energy of molecules. This is elementary, but I like the visual because I feel like it's going to help us understand things that are more complex. So here's what the directions are. Spread out, and then everybody's just going to walk in a random fashion, but the rule is you only take 1 step every time you hear the drum beat. Those rules make sense? so everybody's going to try it. If I do this, you take a step, right? And then if I do it again, you take another step. It's okay if you bump into each other. So right now, this is a low energy state. I'm the energy. The energy is powering the system. When you have energy, you can do kinetic things.
Every time I did it, I'd always like.
All right. How we doing, gang? We're okay?
We're a little.
Who's hot? Just kidding. Don't care. We're all hot. Okay. So, the movement of particles is exactly like the book, and all of the engineering and physics that we just did, all of that molecular stuff that we just talked about, and when we looked at the book moving, all of that we said is true for molecules as well. So we can measure that. We can see how molecules are moving around, and we can look at the kinetic energy. The movement of molecules is the same, and so there's force pushing it, and there's distance, but we're going to measure the movement of molecules with this standard called temperature, which I think everybody knows. You guys feel that? So temperature is the measurement of heat energy. So now we need to break heat energy down a little bit. There are three types. And we're going to do this in a reverse order that you had in the reading, because I want to do it in a specific way, keeping in mind that we're driving to how does climate work? How does weather work? What drives everything on our planet? Literally everything. Let's start with radiation. The sun, by the way, is unbelievable. You feel how it's hot out here? But just use the sun for our lectures. It's perfect. It matches. Well, where does that heat come from? This is how it looks. The sun pumps sweet energy towards us all day, all the time. Nuclear fission is happening. It's extremely hot. It's pumping out all of this energy. It flows 93 million miles towards our planet and strikes our planet in the form of photons. So I drew here the sun, and then I drew the earth and a tree, and there's some grass and all that. And the energy from the sun is coming down in this thing called photons. So the photons that are released by this nuclear fission that's occurring in the sun, which is extremely high energy, has the ability to light electrons. I want to make sure that this part is really key. The heat that comes from the sun, it's not pumping heat towards us. The heat comes from this source. The photons flow into matter that is on the planet already, and most likely things like the ground or this tree or this sidewalk or this grass, and it excites the electrons of the matter. So the matter is absorbing the energy from the photons, and then it's releasing energy in the form of heat. So make sure you understand that process. The radiation is coming from the sun in the form of photons, but the heat isn't coming from the sun directly, it's coming from the earth. Some of the energy, by the way, it comes in light, which makes day. Some of it is reflected off items, and so we see color and we see all kinds of things in our world in the visible light spectrum. Does this make sense so far? Okay. So items on the earth reflect some of the sun's energy. And this is a definition that I didn't write down, but you should know. The word albedo. A-L-B-E-D-O. A-L-B-E-D-O. dO. And that refers to how much of the energy is reflected. So things that are white, as an example, will reflect more of the light. Things that are dark will absorb more of the energy and then release the energy in the form of heat. That's where heat comes from. So all of the heat that keeps our planet in this nice cozy range for things to exist and for us to be hot in this moment right now, it's not from the sun directly, it's from radiation into the earth. The earth absorbs it and releases it in the form of heat. We feel good about radiation so far? Let's go to the next definition. Next, conduction. All matter has the ability to conduct electricity. That's not accurate. Has the ability to conduct energy, meaning energy can flow from one item to the next. But some items can do that much more efficiently, things like metal. Air, by the way, cannot do it very efficiently. Metal probably does it the most, which is why I drew some power lines. So one form of energy is electricity. We use metal like copper oftentimes to send electrical current, and it's a good conductive metal, and so it can facilitate the flow of energy from one place to another place. So that's what we're talking about with conduction. But this process from the previous page still has a role to play. So radiation, the sun's energy comes down in the form of photons, goes into the earth, and then it's released in the form of heat. And so the heat that's out here is conducted from matter that's on the earth's surface, tree, ocean, lake, river, sidewalk, rocks, all of that, and it's conducted from there into the air. At the beginning of this, I said some matter is not very good at conducting energy, but some is really good. What is not very good at?
Rubber.
Rubber's not very conductive. What state of matter is probably not very good at conducting? I said it out loud. I just want to see if anyone caught it. Gas, air, right? So we have some conduction, some movement of heat energy from the earth to the air, but at that point, conduction starts to cease because air is not a very conductive state of matter for thermal energy to flow. Does this make sense so far? So the chain of events for heat on our planet, radiation to conduction. Does this feel good? I'm ready to move to the last piece. Check it out. I ran out of paper on my sheet when I was making this, and then I thought, oh look, this one I'll just have to write on the cardboard. And that worked out in my mind because I thought, well, it looks different. It looks more memorable. Maybe you'll remember the cardboard page. This is the most important page. Convection, which is what we're going to talk about now. Convection is also the flow of heat energy from one place to another place. What time does class end, by the way? Anybody know? 25? Oh, we're killing it. We're killing it. Okay, so conduction or radiation to conduction, and then now we're going to look at this thing called convection. So we're in the air, which can't continue to conduct the heat very well, but we want to move from high energy to low energy, which is the state that all matter flows that we talked about yesterday. So we have energy flowing always from a state of high to low. High to low. How does it go? From high to low? Everything is always... How does it go? High to low. You got it. So heat energy is going to go from high to low. But in this sense, since it can't be conducted, and there's no source of energy for it to be radiated, then we have to do it via some other mechanism. And that is convection. So I wrote down here... ignore this for a moment. I'll explain what the circle is. But for things that don't conduct very well, heat energy still flows, but it goes through this mechanism. So this is very important for energy in air, but also in water. And I'm just going to read it exactly as I wrote it. It's the movement of particles due to density and gravity. I'm going to walk it back and forth so people can write it down. Which page is the most important? It's this one. How do things flow? From high to low. But it's the movement of particles that have heat energy due to density and gravity. Standard working definition for density. Who can give it to me? Just an easy, quick definition for density. Yeah. The amount of stuff in a given area. So if I have more stuff crammed in, so if I have like a meter cube, for example, and I have a lot of stuff jammed in there versus not a lot of stuff, which one is going to be subjected to gravity more, the heavier one or the lighter one? It's kind of a trick question. It's about the same, right? So that's kind of an interesting thing, right? If we're talking about air and water, though, we're packing it in and we're putting it into a small space. So within the sphere of matter that you find it, in air and water, it takes on this property of being heavy. So when we were out here and we were doing the drum thing, when we were a cool state, all the molecules were kind of packed together, and then we started putting energy into the system, and the kinetic energy made you guys move around, and sometimes there was collision, but most of the time you were getting more and more spread out as we went on. As things get more and more spread out, what does their density look like? It's less dense, right? And so, put this down. When things are warmer, they have less density. And then on the corollary, the reverse is true. Things that are very dense are heavier, and they're going to be more subjected to gravity. Does this make sense so far? Going back to this right here. In air and in water, the agents of change for moving the energy from one place to another is density and gravity. That's very important. By that I mean, so when we were conducting energy, we were just moving the energy from here to there like a chain reaction. And likewise with radiation, it's kind of like a chain reaction. The distinction between convection and those other two forms is now the heat energy is going to move from this space to another space because the particles themselves are actually moving. So now it's not like a chain reaction. I'm going to move from this spot to another spot, and that's due to density and gravity. Okay, I'm ready to show what this looks like a little bit. You guys understand this, but I want to make sure that you have this definition, and then I want to show you something. So, what happens with heat? It rises because of the density getting less, and it goes up. What happens with cold? It falls because of the density. But which thing do you think is more in charge? Is it the heat? Because we know things flow from high energy to low energy. So the particles from heat, is it going to flow more, or is it the density going to be the more important thing? Think about that. I'm going to get... there, we had this water on a hot plate just to make sure there's no tricks involved, like a magician, feel this and confirm to me that it's warm. Red equals warm, okay? So here's what I'm going to do first. We're going to do this in two different ways. On your notes, in some manner, because this is the most important thing, and you already know that, because I've said it many times over now, you should take some observations of what occurs in this system, okay? Before I start, I'll tell you when to take the observation and what all I want you to do. So here I'm going to put just some red, warm water in these flasks on each respective side. We'll do this whole thing twice. I got to fill it up all the way. So this is hot. Now I have a pitcher of ice water here. You can see there's like ice cubes in it. So it's pretty cold. This is cold. So I'm going to put a little blue water in the opposite flask. One for each reaction as well. All right, the setup is exactly the same, agreed? Okay, the first time, I've been telling my 10th grade students, by the way, that the periodic table is like one of the most important tools ever made. I agree with that statement, but I'm going to use it as a tool for this demonstration. It's just like a laminated sheet so I can keep it, but it seems like a nice visual. I thought I would reinforce. This thing is pretty awesome. This can tell you a lot about our universe right here. It's a very important tool. So if I take the cool water, well, let me do it like this. If I take the hot water, and I'm going to invert the jar, hopefully none spills out, and I'm going to put it on top of the blue water. Before I do it, predict what you think is going to happen. Keep in mind, heat flows from high to low. So what's going to happen? Take a second to make a prediction. Make a prediction. Think about it. Anybody want to throw out what they think will happen here? Yeah.
They're going to mix.
He says it's going to mix. What do you think?
They're gonna like switch places.
They're going to switch places. What do you think?
I think nothing's gonna happen.
He says nothing's going to happen. He says nothing's going to happen. Well, one of those things is true, and one is not true. I'm going to leave this here. Actually, come hold it. This is why we have two hands. This is excellent. Okay, now I'm going to do the opposite on this side. Same thing. You already know what I'm going to do. Make a prediction of what's going to happen. So either nothing will happen or a lot will happen. Oh. Okay. Give me a. What do you think's going to happen here? Yeah.
And this one, the blue liquid is going to sink and replace the. It's either going to mix with or replace the rest.
It says it's either going to mix or replace. Yeah. It's going to switch places. Okay. What do you think?
I think it'll stay where it is.
It's going to stay where it is. All right. So let's do this. I'm going to have Mr. Haba do his side first. Make some observations of what occurs. Make observations, and in either case, what could happen might happen quickly. I tried to level the table. Beautiful work right there. Can we get a round of applause for Mr. Haba? Fantastic. Right, okay. I saw a lot of people checking out, but not a lot of observations written down. The observations that you write down are going to be important. Keep it in mind. This is the easiest version of this. We're starting simple, and we're building to more complex. What is? Make some observations, and then I'm going to go with this one. Oh! It's okay. Everyone saw it, right? Things happen. Okay, you guys ready for this one?
Yeah.
All right, here we go. Make some observations on this one as well. Make some observations. You gotta give him credit. It's hard. This is not the ideal setup, by the way. not going to touch the table. I definitely caused it falling over the first time, by the way. So what's happening? What's happening? Yes. They're mixing. Everybody agrees. Everybody can see that they're mixing, right? But how are they mixing? Is the hot going up or is the blue going down? The blue is definitely going down. The blue is absolutely the one going down. Let's take it back to convection here for a moment, shall we? It's the movement of air or water and the agents of change. Heat energy always flows from high to low. The good thing is I'm not going to ask you to memorize a new thing because it's always high to low. But the agent of change is density and gravity. So the dense particles that are the cold ones are packed together. They're more dense, and gravity is pulling them towards the earth. So even though, yes, it's true, amazingly, if we took the temperature, this jar is getting warmer because heat energy is flowing from here to there, but it's flowing in a really slow way. It's flowing via conduction, but water is not very conductive, so it's not very efficient. But the heat is being exchanged in a fast manner, but it's due to density and gravity. Does everybody feel good about that? Now, here's the final culminating point for the class today. Any questions on this before we wrap it up? I'm towards the end. We're almost done. Any questions on convection? This is the real deal. This is the big thing right here. Where does the heat energy on our planet come from? The sun. So where is the most heat energy being generated, or where does the most heat energy exist? What place on Earth? Where is the most heat energy? Where gets the most sunlight? The surface of the Earth. That's a right part of the answer. And that's part of the answer. The surface of the Earth, which could be the ocean, by the way. But where geographically? I think Jack had his hand up first. The equator. So at the equator, this is the big deal right here. Energy is concentrated. It's coming from the sun into the earth, ocean or land, mostly at the equator, and then it's flowing from those objects. It's absorbed and then it's released in terms of heat, and it's conducted into the air. And once it's in the air starts rising because it's warm, and it goes up into the atmosphere, and it moves around. So the movement is going according to density. And then cool air is falling back towards the earth, or likewise cool water is going down towards the center of the earth because of density and gravity. Does the link between energy, radiation, conduction, and convection make sense? This is the easiest day of the most complex part of our class. Make sure you feel good about these things. We have a few minutes left to go. So, perfect time for announcements. Let me stop the recording.